Good evening, everyone. Welcome to the next live session. Wait for people to join. I will request people to ask your questions by typing it in the chat window. What I have displayed here is what we are learning in the 5th week. We have moved from sources to the properties of the channel. Now, in a fiber optic communication system, the channel is nothing but an optical fiber. So we started by discussing a very simplistic picture of light guidance. What you learned in your high school, the mechanism of guidance with TIR, the total internal reflection. Then we said that once we know what is the allowed angle at the interface, we can then calculate what is the allowed angle at the input, and then we worked out what is the largest angle that can be launched. So that gave us the idea about numerical aperture of the fiber. The next important thing we learned is that even though the angle of incidence, let's say here, theta I, even when this theta I is greater than the critical angle, that should allow total internal reflection. Not all angles greater than theta I are allowed. We moved from the ray picture to the wave picture there, where we said that, look, only those directions are allowed where the light is allowed to undergo constructive interference. So we worked out what is a phase condition for that, and that actually paves the background of why do you need or why do you have modes of a fiber. So modes, in a sense, by strict definition, it is the solution of possible solutions of Maxwell's equations, wave equation, subject to boundary conditions. We had talked about this boundary conditions in case of a resonator. There it was longitudinal boundary conditions, right? You had the boundary on either end of the propagation. Here we are talking about transverse boundary condition. And what is this boundary condition we are saying? We are saying you have an N1 and you have an N2, which is less than N1. So in this direction, in the transverse direction, how is your electromagnetic wave confined? And because of that, what is the nature of the field distribution? So at the end of the day, the modes will tell you the specific electric field distributions that are supported across the cross section of the optical fiber. It's important to understand this because depending on the number of modes you have, you will have intermodal dispersion, you will have attenuation, etc. It all depends. The walk off between the modes will decide what is the fastest bit rate you can transport and so on. So all that we will consider when we are doing dispersion next week. So this week we were focusing on how to mathematically calculate what the transverse profile was. The mathematics is a bit tedious, and I had intentionally tried to keep it as as elaborate as possible. I have not missed any steps so that you can go through and understand and appreciate the mathematics. It was just that the Maxwell's equations turned out to be a Bessel differential equation, and the solutions are Bessel functions. And finally, we calculated the LP, supported LP, LM modes of the fiber. And through the 4 or 5 lectures, I gave you a recipe to calculate what is the effective index or the beta of each of these modes. That is what is different. So what is different in all these modes? One, their transverse profiles are different. So if you have a camera and if you can take a photograph of the transverse beam profile of these modes, they are going to look different. Then the theta or N effective, which is the effective refractive index. So we did this in the class. I explained this to you. This is, let's say, N1 and this is N2. What happens is the different modes will have its propagation constants or will have its effective refractive index, which is effective speeds that are decided by wavelength, by this N1, N2 difference and so on. So this is as a function of R that we are saying, but it doesn't matter. The, the modes, so for example, this is the fundamental mode. The fundamental mode is the most confined mode, which is whose the refractive index seen by the fundamental mode is as close to N1 as possible. So we figured out the recipe as to how to calculate this N effective for each mode. So we spent a lot of time in understanding the mathematics. So I would request you to please go through the mathematics, write it by yourself to appreciate what we are doing. But at the end of the day, this is what we did. We said that for a given fiber, you have N1, N2, A, and for a given lambda, which is which we are trying to launch into the fiber, there exists a number called V, which is the V number, right? And this V number is 2 pi by lambda. This lambda is in free space, A root of N1 square minus N2 square. So this defines the characteristic number called as V number for the fiber. And what is interesting to see is that this V number is not a constant for a fiber. It depends on what is the wavelength that you are propagating through the fiber. So the recipe goes like this. You first find out V, and once you have your V, you also have to need to have the knowledge that you can have LP, LM modes with L is equal to 0, 1, 2, 3, etc. And then we wrote a transcendental equation, and there were M solutions for the transcendental equations for each value of L. For every value of L, so you start trying to plug in this different values of L in each in that transcendental equation, and you will realize that for any value of L, there could be M solutions. Sometimes the solution is 0. In this case, there are no solutions, in which case no mode is supported. Depending on the V number, we did derive the two transcendental equation, two sets of equation actually. One equation for L equal to 0 and another equation for L not equal to 0, right? We had derived this in terms of Bessel function. It looks a little complicated, but that's okay. I mean, we don't have to mug up anything. We know that this is how the solutions do exist. So once you solve this kind of now there was a question somebody asked, that what is a transcendental equation? Now transcendental equation is something of the form, let's say tan x equal to x kind of equation. Now you can't say x is equal to tan inverse x, right? So how do you solve such equations? You say one way of solving that equation is to plot. You plot the left hand side and you plot the right hand side, and wherever the left hand side and the right hand side intersects, those are your solutions. So similarly, there are two transcendental equations corresponding to L equal to 0 and another set of equations corresponding to L is not equal to 0. You solve them for different azimuthal variables, azimuthal mode numbers, L equal to 0, 1, 2, 3, etc. And you get m possible solutions. And once you get these m possible solutions, you can find out the b for the m possible solutions. That's what the transcendental equation solution is given to you. Once you know your b, this b is related to n effective. You can find out the n effective and beta. And you also know that the transverse profile, the transverse profile can be written in terms of JL U R over A, and then there is a cos L phi, and then there is a sin L phi possible solution to it. And this U is ultimately decided by your N effective. So that is how you work out what are the different possible transverse profiles. So this is what we did last time. Now, if you have any questions, please type it in the chat window, either for this week or for the previous week, or whatever content we have done until now. I will wait for your questions. I'll also wanted to point you to a MATLAB code that is shared. There's a small write-up also for the MATLAB code, where we have actually shown how to solve that transcendental equation. So you can play around with the numbers there and find out what the allowed modes are. One thing you need to be careful while using the MATLAB code is that is the following. Let me just try to show you that. So I hope you can see the code right now. So the transcendental equations, as you know, are different. Probably the size is a bit small. Let me see if I can increase the size. Well, it's not looking bigger in my. I can't project it bigger. All I want you to point out is that you have two sets of transcendental equations. The first set, the LHS and RHS, which I'm highlighting right now. This is for the case which corresponds to L equal to 0. Now, you can also have another set of equations which is corresponding to L equal to 1. Okay. Now, when you plot this, I've just run it for a particular V number. You're getting some solutions like this. What you want to, the blue curve actually represents the left hand side, and the red curve actually represents the right hand side. So it will look, when you just look at this MATLAB plot, it will look as if, there is an intersection here. I hope you're able to see my pointer. There's an intersection here. Let's see if I can mark that. No, I'm not able to mark that. So let's take this case. There's an intersection here. There's an intersection here. There's an intersection here. There's an intersection here. So this looks as if there are 4 solutions. So don't be misled by this. You see this vertical line, here next to 0.2, and the other vertical line next to 0.8 or 0.85 is created by MATLAB. It is going from minus infinity to plus infinity. So it's just drawing a line from minus infinity to plus infinity. That's not a solution, okay? So the solutions are here, actually only 2 solutions. There is one solution here which is corresponding to something like 0.9, and there's another solution here which corresponds to, let's say, 0.4. So don't be misled by that. It's you can figure out a way to actually tell MATLAB not to plot that line, but then I think we've not done all that hard work, right? So for example, here in this case, how many solutions do you see for L equal to 1, for instance? You see, this is a legitimate solution, which is corresponding to point something like 0.7. Whereas here, for instance, in this at this point, it's not a solution because it's just cutting that line which goes from plus infinity to minus infinity. So that's not a legitimate solution. Whereas this seems to be a legitimate solution. Okay. So this is for the case for L equal to 1 for this particular V number. I think I had put the V number here as 6, for instance. Now, if I calculate this for, let's say, L equal to azimuthal number corresponding to, let's say, 5. I want to find out, are there any LP phi phi m, LP phi 0, LP phi 1, LP phi 2 kind of modes. So let's just run this quickly. And let's look at the plot corresponding to L equal to 5 for this. So for L equal to 0, you have the same set of solution, nothing changes. But we need to look at what happens when L equal to 5. Probably I did not calculate that. Oh, I actually seem to have deleted that part of this in my program. Let me just open this once again. Hold on for a minute. In the meantime, please type your questions. Okay, so here we go. Let me present this once again. I had by mistake deleted that part of the code. So I let's run it for L equal to 5, and when I run it for L equal to 5, this is what I get. Sorry, this is not L equal to 1. The title is it's wrong. So this is L equal to 5. I have actually calculated it for L equal to 5, but here in the title I had to put it as let's see, L equal to 5. And if I do this, what I get is a result where I do not have a solution for. So this is for L equal to 5. You see the LHS and RHS are not intersecting, which means for I don't have a mode which starts with L equal to 5. Of course, L equal to 0, there is a mode. So there is this I will call as LP01 mode. This mode I will call as LP02 mode. Okay. Let's check if there is something called as LP2 modes here. Anything which starts with LP2. This is again L equal to 2. Yes, you have LP21 mode here, but nothing more than that. Right? So this is how you can actually now find out the B value. And once you know the B value, you can get back to find what the N effective is. Once I know the N effective, I can find out the exact transverse profile. Okay, so I hope that part is clear. You have to don't blindly follow this MATLAB code. Use your discretion to find out, to eliminate those artificial lines which MATLAB is generating. Okay, now I can start. I've started seeing some questions, so let's take those questions. The first question is from Michael Jordan. Does the coherence length has any role with respect to communication? Because 10 gigahertz modulated laser will have just few centimeter coherence length. Having that much coherence length and doing communication or mainly phase modulated data, is there any effect on the data? So this is again a very interesting question. Um, you know, uh, Coherent communication with phase modulation is something that is very new, or rather relatively new in optical communication. So we have to keep asking ourselves these questions, and we have to keep finding answers for these questions. So like what I said last time, let me repeat what I said last time. Let's say I have on-off key data, OOK data, right? Where my intensity is going from 0 to 1. And let's take the case of 10 gigabits per second. So that is 0.1 nanosecond, which is 100 picosecond is my bit duration. If this is the case, then I don't have to worry about the phase of the carrier. Okay, I don't have to worry about the phase of the carrier. I don't have to worry about any coherence link because it is just on-off key data. When this light falls on a photodiode, right? The photodiode just sees the intensity. We will see how the photodiode will detect. So my intensity is the current photocurrent will be proportional to the light intensity. So my photocurrent, or I can convert this into a voltage. I will have a voltage which goes high and low depending on my intensity. It doesn't matter what the phase of my light is, so you don't have to worry about coherence length. So I hope that part is clear, which is why for the last 30 years, we were using optical communication without really worrying about coherence length or line width. Of course, we did worry about it when we were, for example, when we were doing a direct modulation, for instance, we were worried that the different frequency components, because of the chirp of the laser, that can propagate with different speeds, and that can create a spread in the OK pattern. Now, what happens in phase modulated data? Let's now take a look at BPSK data, simplest phase modulated data. Okay? Now, in BPSK data, what you're doing is the phase is getting modulated between 0 and pi, right? It's a phase. This is the phase that changes between 0 and pi as a function of time. So if I have a light a laser like this, right, which is supposed to be exactly coherent, right? This is one way of visualizing coherence. As a function of time, the phase of the sinusoid is maintained. Now, if I say that, okay, let me just use this part of bit slot as 0, and from here to here, let's say, let me change the phase intentionally, and I change it to pi, right? This is what I will do. Sorry, so this is 0. So I have shown pi and 0 here. It doesn't matter, right? It's binary. So let me modulate this with 0. This is with pi. And again, if I'm trying to modulate this with a 0 phase, which means that I will come back at this point. I will come back to this phase. for this bit duration. And let's say again I'm trying to modulate with pi, then I'll have to switch the phase of this light by pi. So what am I switching here? I'm switching the phase of the carrier, right? So you will need to maintain coherence within this time. It is not really the length that you are looking at. You are looking at, of course, the time can be converted to length and vice versa. But what you are more concerned about is during my bit slot, I don't want the laser to change its phase. I don't want the laser to change its phase by itself during my bit slot. I don't want a very badly coherent kind of laser, right? So more than the length, I would look at the time and compare the coherence time with the bit duration. I hope that is clear. Uh, Probably what you are thinking is that if I have a laser, this is my carrier, and if I modulate it with 10 gigahertz, I will get something like this. This actually spreads the frequency, right? This is actually spreading the frequency in the frequency domain. We have learned that this is at 10 gigahertz minus 10 gigahertz with respect to the carrier. And what you're probably thinking is that I'm spreading my carrier. My bandwidth is increasing actually because of this process of modulation. Is that going to affect my coherence length, right? So the point to look at is we look at it in terms of how the phase, how the what is the coherence time, like what I explained here. What is the coherence time with reference to the bit slot? My bit slot. So it's in a way it's related, right? So let's say, let me redraw this once again for you. This is 10 gigahertz. Now let me say I have a coherence time, which is something like this. You see, I intentionally drew discontinuity there. I mean, this is how it we can visualize that it is happening. Now, if my bit slot is like this. Here is where I wanted to do pi modulation, and here is where maybe I wanted to do a zero modulation, and here is where I wanted to do my pi modulation. So zero modulation would mean that the phase should be retained as zero, but you see here there is a phase discontinuity. Now the receiver, of course, we will learn in the receiver section as to how you are going to detect the phase at the receiver. But in the receiver, I am seeing a phase change here. So the receiver has seen a change in phase change here. So the receiver by mistake is detecting it as a phase change, and so it will say there is a bit that has changed state there, and the receiver is going to give me a wrong information. So yes, increase in spectral spread would actually mean a decrease in the time domain. So if I keep going through decreases in time domain rather than increases in time domain, if I do my faster modulation, actually my trouble because of the fact that the laser is not coherent will start becoming lower and lower. It's slightly counterintuitive, but the point you want to look at is within the bit slot, whenever I'm making a decision, is a laser phase constant or is it varying? So I hope that point is clear. So the simple answer to your question is, rather than looking at coherence length, what you want to look at is coherence time. If you have any other questions, please type in the chat window. anything else that was ambiguous in my explanation? You want clarification? You want to ask something other than what we discussed? Please go ahead and ask. Maybe you can type out how many lectures have you seen in this week. Each one of you can type that out. Not seeing any responses yet. Okay, Devdatta, 4 lectures you have watched. Are you comfortable with the contents of the 4 lectures? Do you have any feedback on uh, when this session needs to be conducted? Do you think that having this session on, because I see that the Wednesdays are the days where you have to submit your assignment. Uh, so do you think it'll help if the sessions are held on Tuesday evenings rather than Friday evenings? I will be happy to shift. I have no problem with that. Do you have any such feedback? Do you think it will be better if we have this session just before the assignment submission? You can also ask me to, solve any assignment problems from the previous assignment. If you have not understood, of course, the detailed solution is already put up. But in case you have not understood any content, you can tell me now. You can also tell me, as I said earlier, if you want this session to be shifted to Tuesdays, because I realize this again, somebody pointed out that uh, Wednesday is your last day for submitting the assignment. So if you have any questions related to the assignments, you can ask me. I will not obviously solve the assignment for you just before the assignment submission, but I can provide hints if you have tried and you're not able to uh, reach there. I see a response which says would be better. So you have to clarify what would be better. I mean, are you saying that the Tuesday is going to be better? I'm sorry. I mean, this is not an interactive way. I mean, there's no way you can turn on your mic and speak, but please type in the chat window. So can you clarify what would be better? Live session Tuesday to clarify your doubts. Okay. I can do that. I will request the NPTEL team to see if this can be rescheduled. Is this time okay? 5 o'clock? I don't want to do it in very late in the night because you don't want to be solving your assignments also just at the last minute. Would you like to have a session this coming Tuesday? Assignment 5 needs MATLAB, but you can use it. You don't need to have MATLAB. You can solve it in C or any programming software. All what you need. You can even use Excel sheet provided you can program the Bessel functions in that. All what it requires is Bessel function solutions. Devdatta says Saturday we can clarify our doubt and we have some days to solve these problems. Devdatta, the idea is, let's say you, for example, assignment 5 is on submission is on Wednesday. You would have you would have finished the lectures and you would have started solving the assignments. And what we can also achieve in this live session is that so by Tuesday, I imagine that you would have attempted all the questions and you're getting stuck somewhere, right? And if it is on Tuesday, you can come and you could have safely. I can say you have safely finished all the assignment problems, and then you can come and ask me, okay, in this problem, I was not able to proceed. Tell me how to proceed. I will obviously not give you the solution. I'm not going to give you an answer, but I can point out or tell you the theory or tell you how it's going to be helpful. The theory that's going to be helpful to solve that problem, which is why I said Tuesday rather than Saturday. Anybody else has any objection for Tuesday evening? Any strong objection? Of course, there are only 12 people here. Maybe I'll request the NPTEL team to get this input. On maybe you can conduct a poll and because I was not aware that the assignment submission is on a Wednesday. So if it is on a Wednesday, it's better that I do this live session just a day before Wednesday so that you have sufficient time to go through the content. Same time, it's at 5 o'clock. I don't want to change the time. I will cross-check with the NPTEL team if there are any other technical difficulties, and I'm assuming that there are no technical difficulties in doing this. Mahesh, are you there live? Yeah, do you see a problem if we shift this session to Tuesday evenings? Okay, so Mahesh says no problem. So 5 o'clock on Tuesday. Do you? Let's do this. This coming Tuesday, we will have a session where we will just revise all the content from assignment 1 all the way up to assignment 5. Because the content of assignment 5 we just discussed. I showed you the MATLAB code and I showed you how to run this code and so on. So what we will do this coming Tuesday is kind of just basically revise what we did for sources, and you can come up with all the questions that you have had until the week 5. Does that sound all right? I have issue to solve numerical because right formula. So ANR, I don't understand this. You mean that you do not, you're not able to find the right formula? You see, the idea should not be to write down the data and find out which is that formula which will fit into this data. In real world, you're flooded with data, right? You can't keep finding out formulas. Nothing comes as formulas in the real world. You have to ask yourself this question: if I were to solve this problem, what is the information I need? Let's say, for instance, I have to find out the from last tutorial. Let's say, for instance, I have to find out what is the Vpi of the modulator, for instance. So, what is the information I need for calculating Vpi? I need the voltage at which the output was maximum. I need the voltage at which the output is minimum, because the difference between those two voltages is the Vpi definition. Now I look for that information in the problem. The problem may have so much of other information. So don't try to fit in all what you know with all what formula is. Try to think to be able to calculate this. What is the information that I need? And so what is the, how do I approach it, right? If you can specify a particular question, I can explain. If you can specify a particular question where you face the difficulty, I can probably explain to you. Saying, okay, do that, but you have to tell me the question number only, then I can do that. I can give you an example of a specific solution. Okay, I'm not getting any response. So I'll wait for 5 more minutes, and if there is nothing, we can close. So assignment 5 does not require MATLAB. I am just showing you an example done through MATLAB, but you can do that through a C code also. Yes, sure, Vaidya. So we will center our discussion around the assignments. Again, I will warn you, I will only answer your questions. I will not start by saying, look at question number 1. What do you have to find out? This is what the formula you should use. That's not what I would do. I would again want an evidence that you have tried, and I want you to ask me questions about the assignment questions. Then I will answer. I am not going to spoon feed saying that this is question number one, this is the data, this is the formula to be used, and this is the okay. So there is a Kanchan has a question. In the question where phase error is asked in degrees, I got the answer as 2.86, but the range given is up to 2.82. Let's check that. I hope you're talking about assignment 4. Okay, 2.7 to 2.8 is what is the angle in degrees. What are you saying? You want the answer, you got the answer as 2.86. Why would you get the answer as 2.86? Because these are very, very exact answers. Because you have 10 megahertz, right? So let's look at the solutions that's already put up. The range is 2.5 to 3 actually. So this is going to get regraded. Answer is 2.8. 2.5 to 3 is what the range we have given. I think there is a communication gap. So the answer range accepted is 2.5 to 3. So you should get your credit. So we will make sure that it gets regraded. ANR says how to explain how to use this code. So I can maybe spend next 5 minutes explaining how to use this code. So let's get back here. So what is the code doing? The code is solving the two transcendental equations, right? Which are the transcendental equations? Okay, let's go to the assignment sheet itself, where we have given the writer. I hope you're able to see my screen. So these are the two transcendental equations, right? For L equal to 0, as I said earlier, you want to solve this v root 1 minus b j1, which is the Bessel function, v root 1 minus b. This is the argument of the Bessel function divided by j naught, which is another Bessel function, v root 1 minus b is equal to minus v root b k1 by k naught. K1 and k naught are again Bessel functions, which of the k functions, right? This is for L equal to 0. For L greater than or equal to 1, which means for all values of L other than 0, what you have is to solve this equation. So as I said earlier, how do you go about doing this solution? So first you check, you have to plot the left hand side and the right hand side of this equation. Plot the left hand side and right hand side of this equation, and you find out what is the intersection. So what against what are you plotting? You have to plot it against what is the variable here? The variable here is b. So you have to plot it against b. How do you know the value of b? B is known because that's the b number of your fiber, right? So you have the data corresponding to N1, N2, core diameter, etc. You can find out wavelength, etc. You can find out what is the value of b. So against b, you're plotting the left hand side of this equation and you have to plot the right hand side of this equation. So how do I do that? So here, this is the MATLAB code. I hope you can see this code. Let me try to close these windows. I hope you're able to see this. Okay, you can zoom in your screen. Okay, so let's say you want to calculate this for b equal to 6, right? So you have substituted b equal to 6 here. B is a variable, so let me just try to get in a mode where I can type. I don't know whether I can increase the font size here. Let me try that. I don't think there's an easy way to increase the font size here. What I can do is to make it close all these unnecessary windows. Yeah. Right. So hope you're able to see this screen. So we start with v equal to, let's say v equal to 6. Okay. Now b is a variable, as I said, and we have learned in class that this b will vary only. It's a normalized waveguide parameter. It will vary only between 0 to 1. No other values of b are allowed. So I'm just creating a running variable which is from 0 to 1 in steps of 0.001, which means I'm taking basically 1001 array of size 1001, and I'm assigning the value of b to be 0, 0.001, 0.002, 0.003, and so on, all the way up to 1. So that I'll get a good accuracy of up to third decimal place when I'm calculating this. Now, what you do is, so this is for L equal to 0. So first you say I'm at L equal to 0, right? Now the LHS of the transcendental equation, you remember what is the LHS here? It is v root 1 minus b for L equal to 0. So I'm declaring another variable which says v root 1 minus b. So I'm going to say that vb is v square root of 1 minus b, and this is an array because b is an array. Then you are actually calculating the left hand side, which is vb, which is this v root 1 minus b times, there's a dot star because you're doing the operation, you have to multiply the operation with an array. Bessel j, that's the function which calls for calculating j1 comma vb divided by j0 comma vb. So that is actually basically calculating this j1 and this one we have declared as a VB variable divided by J naught VB variable. Right? This is a variable right now because B is a array right now for me. Right? And that is my left hand side. Similarly, you can do the right hand side. Now, in the right hand side, what does it require? It requires B root B. It is not B root 1 minus B, it is B root B. So I am recalculating that value here. VB for the right hand side is V root B. And then I calculate the right hand side, which is VB, which is V root B. Again, this B minus V root B times K1 and K0 and so on. So that's what is calculated here. So this is actually, it has to be, the right hand side has to be negative. This has to be negative. And then you plot the left hand side and right hand side versus B, and that is what you will get if you run this. This is what you're getting. So this is L equal to 2. Actually, I should look at L equal to 0. So if I put this negative sign and plot, what do we get? Yeah, this should be the correct one. Because you see there is a minus sign here, and I had missed putting this minus sign here. Anyway, so how many solutions are there? As I explained to you earlier, if this Bessel functions actually go to from minus infinity to plus infinity for certain values of b. So this line actually corresponds to where it is blowing up to infinity. That's not my solution. So I should not take this as a solution, but I can take this as a solution because that's a legitimate point. Similarly, I should not take this as a solution because this is a point where it goes from minus infinity to infinity. So you can actually change the y scale here to y limit instead of minus 15 to plus 15. If I put minus 150 to plus 150, you will still see that value you see, this is what I was saying. It's actually because the left hand side is actually blowing up to infinity, and then at that point it's starting from minus infinity. So don't take care of this as the point of intersection. That is not a point of intersection. This is the point of intersection. Okay? So you do that for L equal to 0, and you do that for similarly you calculate what is this function and this function for L is equal to 1. You can plot the left hand side and right hand side, and you can find out the points of intersection, and that will be your allowed values of p. So is that convincing, ANR? Any other questions? There are no more questions. We will close the session, and we'll meet again on Tuesday with a revision of the first 5 weeks. Mahesh, we can close the session. All right, see you later.